Hi, so I'm Paul. I'm a technology evangelist for Instacluster, which is a company based in Canberra. So I apologise in advance. I'm probably slightly jet lagged still. I noticed the first day I was in Berlin, I was using my Google Map application on my phone, and it was thinking I was going in the opposite direction to what I was. So I think it thought that I was still sort of down under and 180 degrees out of sync. And my brain is a bit like that still, unfortunately. So this is quite exciting, talking in a machine learning track at ApacheCon. It's actually, I was thinking back, the last time I was at a machine learning conference was 1987 at UCI. It was the 4th International Machine Learning Workshop, and I was doing my PhD in machine learning at the time. And I didn't finish it, and I ended up doing software engineering research and distributed systems. And it's sort of interesting that 32 years on, I'm giving a talk with machine learning flavour, and I think there's an interesting convergence, because part of the problem we had 30 years ago with machine learning was the computers just weren't powerful enough, and you couldn't connect multiple computers together easily. Well, you could, but it was really hard work. But now there's sort of a convergence of some of the scalability technologies, including things like Kafka and Cassandra, with some of the machine learning research, which actually gives you the ability to do really scalable machine learning type things. So I think there is a connection. So I hope I'm not too much of an imposter at the machine learning track, and that there's some benefit in this talk. So because I'm a technology evangelist, I sort of get to play with some of the technologies that the company I work for, Instacluster, hosts on cloud providers. So in particular, Kafka and Cassandra. So I get to sort of learn the technologies myself. I didn't know either of these technologies 2 years ago. So I had to learn them. I then had to think of an interesting use case for them, and then start to build an application and get it working, and then blog about it and even talk about it in some cases, like today. So this first talk, I'm actually giving 2 talks today. This first one is based on the most recent work that I've done over the last 6 months. So it's the most up-to-date, hopefully the most relevant. There's a talk I'm giving again, I think at 2 o'clock this afternoon, which is some work I did just using Kafka for an IoT application, which I did last year, so it's a bit out of date, but that was my first attempt at learning Kafka, so it's got a lot more about some of the mistakes I made, hopefully, and what not to do. So let's get going. So here's the overview of this talk. It's going to have 6 parts. The wow part, the headlines, why did we do it? What does it do? How does it work? How well did it work? And finally, some so what sort of issues. First of all, the wow part, the headlines. So I'm sort of doing this back to front. I'm giving you the results first, and then explain how we get there. So 50 years ago, it was quite a significant year in the history of the world, particularly in the US. Sorry, European people. This is a bit US focused. I gave this talk in ApacheCon in Las Vegas last month. So I don't think Elvis is coming home again anytime soon, but sure enough, man did walk on the moon. And there was this funny festival thing that took off, and there was a new president and a few other things like that. So yeah, man walked on the moon. That was pretty exciting at the time. I remember it. This other thing, some 3 days of peace and music, Woodstock. 50,000 people were expected. That was how many tickets they'd sold in advance. 1 million people actually tried to get in, and about 500,000 people actually were there for some of the time, they reckon. So it was a pretty big event. Fast forwarding 50 years, we announced the results of this project a couple of months ago. We had a press release, and it got picked up by quite a few agencies. I was quite pleased that people were interested in this type of topic, and the sort of the headline that we had, 19 billion anomaly checks a day. But is 19 billion anomaly checks a day a lot or not? Well, depends a bit. Let's have a look at this in terms of a more traditional transactions per second metric. So in terms of checks per second, the system that we built could achieve 220,000 checks per second. Well, it's a slightly lower and less impressive number, but in terms of the daily throughput, it's the same thing. I had a look around for some similar results. So these aren't exactly the same in terms of how they achieved them, but they did use a similar technology stack to us. They used Kafka, Cassandra, and Spark, and there was some actual machine learning going on and model building, but they only managed to achieve 440 checks a second. So we're a lot more than that, so that's sort of exciting. Parts of the system actually achieve a higher throughput than that. We've actually used Kafka as a buffer, and that part of the system has a peak of 2.3 million Kafka writes a second going into it, which is about an order of magnitude more than the rest of the pipeline. So in this case, Kafka's absorbing a load spike up to 10 times what the rest of the system can cope with. So that's another big number. So back to the billions a day numbers. Is this big in terms of the planet? Well, yes, the population of the planet is about 8 billion people at the moment. So 19 billion checks a day corresponds to about 2.5 events per person per day. Which seems pretty cool. We did have to stop somewhere. There was, in theory, no upper limit to what we could have got out of this system, and it was sort of arbitrary where we decided to stop. So, why did we do it? What were the project goals? Well, first of all, we had multiple goals, like this slightly obscure Australian game called AFL. Rather than just 2 goals, they had this concept of having 4. I've never understood it myself, but anyway. So the first goal was that we were talking about fast data processing. We wanted to be able to process streams data essentially in real time, which means sub-second. So we wanted the events to come in, run the algorithms, and make a decision in under 1 second consistently. So the second project goal was to do with big data in terms of throughput and size of the system. We didn't want the system to have any arbitrary upper limit to the scalability. And I mean, we actually did want to produce some big benchmark numbers that we could publicize as well, to be honest. We also wanted the system to be cost effective. Essentially, this means that we wanted it to be incrementally scalable so that users could only pay for what they used. So you could size the system for the demand that you expected, and with a high benefit to cost ratio. So if you only need a system half the size, you should be able to achieve that. This is a picture of half a car from an Australian movie called Malcolm. It's quite fun if you haven't seen it. We wanted to use 2 of the technologies that Instaclust offers as a managed service, Apache Kafka and Cassandra. So we had to come up with a use case that used both of these together in some interesting way. So our platform does virtually everything for you, including things like provisioning, monitoring, scaling, and more. So I used those sort of features extensively as I was experimenting with the technologies and tuning the system and finally scaling it for the final results. The other thing we were interested in was using Kafka as a buffer. So this is one of the use cases of Kafka. You sort of get it for free. It acts as a buffer by definition. It decouples incoming and outgoing events. The consumers don't have to be ready to read the events until they're ready, and it will absorb essentially an infinite amount of load for short periods of time. So it's cost effective for short load spikes. It prevents overloading the rest of the pipeline, and all events are eventually processed. So it's fine if you don't have a particularly strict SLA on all the events and you've got some leeway to process some of them later on. The other part of the experiment we were quite interested in was the ability to automate the application, and this came out of my previous attempts to build scalable applications with Kafka in particular. The applications themselves are actually quite difficult to scale, and you want to be able to automate the scaling for those. And the other aspect is observability. So in order to be able to understand the system sufficiently to be able to tune it and scale it and debug it in some cases, you have to have good quality monitoring of the application, not just the clusters themselves. So in order to do that, we decided we were going to use Kubernetes for the application automation, Prometheus for the application monitoring, and something called OpenTracing plus the Jaeger tracer for the distributed tracing. So I've sort of assumed that we know what we're doing, or we don't actually know what it does yet, so let's have a bit more of a drill down into the actual application itself. It's an anomaly detection use case, so it's designed for spotting unusual events. So it was interesting when they did put men on the moon 50 years ago. There were lots of people that got them there, but there was actually only one woman in the Apollo 11 control room. So she was a bit of an anomaly, but a critical one because she was in charge of the monitoring of the Saturn V rocket itself. So the goals for anomaly detection are to spot the difference at speed and scale. So first of all, the speed, as I mentioned, we wanted to be able to spot the difference in potentially quite large amounts of data in under 1 second. So we're definitely talking about something in the space of streams processing, not batch processing at this point. So that determined the type of technology we picked. Scalability was in terms of both the size of a key space and the concurrency of the data coming into the system and subsequently stored. So we were dealing with data that potentially had billions of keys. So we needed a big database to be able to store and query that amount of data. And also for the processing, it had implications for the processing scalability as well. So some of the dimensions for scalability are the load, including data velocity. The load was expected to increase. There was no upper bound, and you would get load spikes as well. The other part of that story is the affordability. Sure, you could build a system that was big enough perhaps to process the maximum possible load spike, but in order to be affordable, you actually have one that has linear resource scalability, so it has to be elastic on demand. You need incremental resources which change with increasing load. There's lots of anomaly detection use cases, which is another reason that we picked it as a sort of application area. In a sense, it didn't matter what the application domain was. People could imagine their own use cases. So there are many and varied, including infrastructure monitoring, application monitoring, IoT, finance fraud detection's quite a big one for this sort of space. Clickstream analytics increasingly, and even odd things potentially like drone deliveries, which have quite a lot of moving parts, in fact. Okay, so the next part of the story is, well, how does it actually work? How is it made? We're going to have a look at the anomaly detection aspect, the architecture, and how the technologies actually fit together to make it work. Is this our machine? This is the audio tally-o count machine from Dr. Zeus. It's actually a streams processing machine for counting sleepers. And to some extent, we have advanced a bit from this 1960s technology, but some of the pieces are actually present in that machine. An algorithm from the same vintage is actually what we chose eventually. It's called a cumulative sum control chart. It's pretty old, it's still in use in some situations, and it's used for statistical analysis of historical data. So it relies upon the fact that as each new event comes in, you can compare it based on the key of that event with the previous events for the same key back to almost an arbitrary amount of time in the past. So it has a number of properties which are quite nice for us. It doesn't assume equal time periods. The events can be quite widely spaced across time. It doesn't require a particular number of events either. The downside is that as new events come in, there can be a bit of a lag between when the anomaly actually occurred and when it's detected, but that's okay. So we picked this mainly because it's not computationally expensive. There's no machine learning required. You don't need... it's untrained, it's unsupervised. There were other alternatives we looked at, but this seemed to fit the bill for our particular problem. So in terms of the logical steps involved, the events are coming in as a stream. These are assumed to be coming from some real source. In the financial sector, it might be coming from the banking systems or from the ATMs or from people's mobile phone apps that are doing the transactions and things. In our case, it was simulated data. So once the events come in, the application picks the next event available from the stream, it writes the event to the database so that it can remember it for the future, and then it queries the historic data from the database for the key of that event. If there are sufficient observations, it then runs the anomaly detect algorithm and makes a decision about whether there's a potential anomaly detected. And in a real system, some sort of action would be taken at that point. You might prevent someone's credit card from being used, which is what happened to me the day before I flew here, unfortunately. So yeah, there can be some real-time action, or perhaps it might just get queued for people to investigate subsequently. Here's the design of the whole pipeline, including the technologies we're using. This shows the interaction between the transaction generator on the left, the events going into the Kafka cluster, the anomaly detection pipeline, and then Cassandra on the right. There's a few details here which turned out to be quite critical. We used 2 thread pools for the anomaly detection pipeline. One thread pool is purely for the Kafka consumer, and then the events get handed off to another thread pool which handles the writes to the Cassandra cluster, running the algorithm and then doing something with the results. So it was quite important to decouple the consumer from the processing part of the pipeline. Yep. In terms of the cloud deployment context, the Kafka and Cassandra clusters are hosted on AWS, running in our managed service infrastructure. The application, the event generator, and the detection pipeline are also running in AWS, but running in a Kubernetes X service provided by AWS. I don't know how much people are familiar with Cassandra and Kafka, so bear with me if you're an expert, but I will just briefly cover some of the important points. So Cassandra, open source, it's an Apache project. It's a NoSQL database. It's a masterless ring architecture and uses partition data for scalability and high availability. It's very fast for writes, not so fast for reads, but fast enough. And it's got a reasonably powerful query language with indexes. We offer this as a managed service. There's some of the advantages there if you're interested in our service. Perhaps I'll just mention we actually do a certification program for Apache Cassandra. So we produce a report which is quite rigorous and detailed based on our actual testing of it and benchmarking, which is some of our customers find quite useful and gives them a lot more confidence in using it in mission-critical application areas. Kafka is a distributed streams processing system. It enables distributed producers to send messages to distributed consumers via a Kafka cluster. Again, some of the benefits are that it's fast, high throughput, low latency, it's scalable, and the same way that Cassandra is, you just add nodes to get more throughput. It's reliable, it's distributed and fault tolerant in the same way that Cassandra is. You can make sure you've got 0 data loss. Again, it's open source, it's an Apache project. Interestingly enough, it was actually designed by LinkedIn to solve their application integration architecture problem. They had a sort of a many-to-many spaghetti type integration architecture, which is obviously unsustainable, and they wanted to be able to essentially move to a hub and spoke architecture model. So the solution that it was designed for really was to get data from heterogeneous data sources and make them available to heterogeneous data sinks. So it's actually really good for that sort of use case as well. And again, it's available as a managed service by Instacluster. So looking at a bit more detail, the application automation was done with Kubernetes. So this was a new technology to me. It was obviously one that's been increasing in use and awareness in the last few years. So it seemed like a particularly good choice to try out. We used AWS X to do to provide the master nodes for it. And we hosted our load generator and the anomaly detection pipeline on the worker nodes. So yeah, this sort of explains some of the story on how the application communicates with our clusters that we manage as well. So we had to use VPC peering to get things to work properly. And also our provisioning API that we have open, which enable people to actually spin up clusters, do things with them, and kill them off again programmatically as well, which is quite useful in DevOps type situations, which is more or less the sort of environment that I was working in, because I was this wasn't a production environment, it was purely a development test environment. So that was really, really handy. Again, I'm not quite sure what level of knowledge people have about Kubernetes. This, at a very high level, it's an automation system for the management, scaling, and deployment of containerized applications. There's a lot of buzzwords in there. It's a master worker architecture. The pods are the unit of concurrency. That's probably the most important thing in terms of scaling the system. Assuming you've got sufficient worker nodes, you can spin up more pods and scale the application up and down. Again, it's open source. It is cloud provider and programming language agnostic, which is perhaps the main differentiator compared to some previous attempts at doing things in the space. You can develop and test code locally and deploy at scale into a public cloud provider. It helps with resource management. You can deploy applications to Kubernetes and it manages the scaling up and down and keeping the application alive. So it's not just about scalability, it's about availability as well. Interestingly, there's more powerful frameworks coming that are built on Kubernetes APIs, and some of them look really, really useful and quite cool, particularly things for the service mesh type environments and things. So I mentioned before observability, so we decided to use Prometheus for monitoring. I've actually got a whole talk which I gave at ApacheCon in Las Vegas on the monitoring aspect, which I think is available certainly on our website, if not somewhere else. So it goes into a lot more detail. The trick turned out to be to use the Kubernetes Prometheus operator running in the Kubernetes cluster itself. That made it a lot easier to get the monitoring to work. We used Grafana for graphing. The built-in Prometheus GUI is next to useless. And the way we used it was essentially to debug, tune, and observe the sort of the top-level business metric that we actually wanted to report on for the benchmark result. So that was just the total throughput of the system, and also to ensure that the response time was sub-second for that reported result. We spun up eventually 100 application pods. So these two graphs actually show, if you look carefully, there's a whole sort of layer of graphs there, and each of those is reporting the metrics for one pod. And this is the stacked result, the aggregate result for all those pods. And it works really well. It scales dynamically. You can scale the application up and down, and it copes with keeping track of which things are being monitored and how many of them there are. Again, I don't know how much people know about Prometheus. I'm not an expert exactly. I've used it once now, and it works pretty well. Here's the high-level architecture. It's for monitoring applications and servers, so it's sort of dual purpose, which is quite handy. You have to have instrumentation. That's the downside. Without the instrumentation, it'll allow you to monitor servers okay, but in order to monitor applications, you actually do have to have some instrumentation in your code, and it's quite easy to make mistakes, as I discovered. It's pool-based, which scales really well. So the Prometheus server, basically, you have to tell it where the endpoints are to get the metrics from. The Prometheus operator does that automatically for you. So you don't have to do it manually, and you just can't for large systems anyway, so it has to be done automatically. So there are all the different components involved in Kubernetes. So the operator, I mentioned this before. So in a production environment, you really have to use this. So it manages the application complexity and, most importantly, the dynamics. So you set it up. There is some configuration initially, but once you've done that, it'll work well. The second part of observability, which perhaps a lot of people aren't familiar with, is the tracing aspect. So this enables you to get sort of an end-to-end viewpoint of the application, either for every single transaction going through the system or at some aggregate level, the sort of topology view level. Now, there are some APM products, commercial ones around, which have done this for quite a few years and quite well. But this is open source, and it worked. I was quite pleased with the results. The picture at the top there shows an example of a single trace of a single transaction going through the system. What I find more useful and interesting in some ways is the aggregate topology view. So it's analysing the data in real time, and then you can basically say, well, show me what the topology of the system at this particular point in time looks like, and that's what the lower picture there does. Even though we had a pretty simple topology for this pipeline, it really is just a pipeline with a couple of different things going on in terms of the interaction with the Cassandra database at the bottom and running the Anomaly detector. It was actually quite valuable for debugging. I mentioned that with Prometheus, you have to instrument your code. In one particular run of my system, I was not getting the results that I was expecting. and I actually wondered whether I'd made a mistake in the instrumentation, and I was able to use this view of the system provided by Jaeger to actually double check that all the calls actually were being made correctly, and so I was able to debug the system quite quickly at that point. Again, if you're not familiar with OpenTracing, it's a standard API for distributed tracing. It's a specification, not an implementation. So in order to get it to work, you need A, the application instrumentation, and B, an actual tracer. And there's a whole bunch of them. Some are open source, some are proprietary, so you can just take your pick. I picked Jaeger. I also tried Zipkin. That worked pretty well as well. It's got quite an interesting internal architecture, Jaeger. It's scalable, and it's got sort of almost a feedback loop mechanism as well, which enables it to tune itself, so it can select the right amount of data coming out of the monitored infrastructure. So yes, it uses Cassandra and Spark in a production environment. So that was a pretty simple example. I actually decided, well, it looks like quite a powerful technology. What can we do with it to monitor a more complex Kafka application? For example, an enterprise service bus, when we might have potentially, pardon me, hundreds of topics and events being consumed, processed, and then pushed back into topics with quite complicated networks. So it actually worked pretty well for a simulated example. So I'll just emphasize this isn't a real application, it was a simulated one, but OpenTracing plus Jaeger did actually produce a good insight into what was going on. So the final part of the talk is how well did it work in terms of the scalability of the system. So I started out with 3 default Cassandra nodes. That's the minimum number that we allow people to run in order to make sure you've got a replication factor of 3. So I was interested in the question of how easy and how far can I scale the system. So there was a bit of work to do even for the 3-node Cassandra cluster system to actually optimize it, which is what I did initially. So I spent some time optimizing that system in order to get the best sort of throughput and the least response time that I could. So this is one of the tricks that I used. It's quite a high read to write ratio, this particular application. For every event you're writing into the system, you have to read 50 or more events back, again, to check if there's an anomaly. So it turns out you can tune Cassandra to cope with that, and that's to do with the compression chunk size. So it's the magic number that I used. Interestingly enough, this car was the first vehicle to reach 100 kilometers an hour in 1899, and it was electric. Isn't that cool? I thought that was cool. So it's a bit like my 3-node Cassandra cluster. It's cool, but it's not the best in the world just yet. In terms of scaling, what can we tweak? Well, the thing which determines the load on the system is the load generator in red there. So there's a knob essentially to change the rate of events coming into the system. The second thing that I could modify was the cluster sizes and the worker pods, and the number of worker pods in the application, which are the orange knobs. And then the final thing, which is a bit sort of lower level, is the thread pools, the partitions, and the connections in yellow. And they turned out to be all more important than I thought. So this graph shows my first attempts at scaling the system out. So one thing about Kubernetes is it's really easy to scale the application. You just increase the number of pods, assuming you've got sufficient worker nodes in your Kubernetes cluster. In some ways it's too easy because you can just spin up more pods without actually thinking about whether the system as a whole is going to work correctly or not. So this was my first attempt. After tuning the 3-node Cassandra cluster to the best that I could, I then scaled it out to 24 Cassandra nodes. And that's the blue line there. As you can see, that was a slightly disappointing result. I wasn't getting the sort of the scalability increase that I was expecting from that. What had gone wrong? Well, basically I was ignoring the settings for the thread pools and the relationship between those, the number of pods and the number of Cassandra connections. So essentially my tuning methodology changed. I tuned each of those things for each size Cassandra cluster each time, and that produced a far better result, which is the orange line that's there. So that was on the Cassandra side. The Kafka side turned out to be important as well. This is perhaps a little known aspect of Kafka, which I discovered the hard way, unfortunately. This is a graph showing the number of partitions in a Kafka topic on the x-axis versus the throughput. So as you can see, as you increase the number of partitions, the throughput drops significantly, which is not a desirable feature of a scalable system. So this is a problem because in my application, the number of pods increase the number of Kafka consumer threads, which results in more Kafka consumers. And in order to have more Kafka consumers in Kafka, you need more Kafka partitions. But unfortunately, it lowers the throughput, which is counterintuitive at that point. What's the solution? At least I hope I've got it here. Yep. So the obvious solution, and the only one that I actually tried, was to make your Kafka cluster bigger, which is sort of like it's the low-tech solution for this problem. But inevitably, it worked. So as you essentially, I was able to size my Kafka cluster to achieve the sort of target throughput that I had for the number of partitions that I needed, which in my case was about 200. So I was able to get the throughput of about 2.3 million writes a second just by making the Kafka clusters bigger. There are some other tricks that I've subsequently heard about, which I, again, haven't tried, but it turns out that in Kafka, the number of replica fetches by default is 1, which seems like a particularly silly number, because at that point, you've got a bottleneck in the system, and as the number of partitions goes up, yep, sure enough, the throughput goes down. So I have read some studies recently that suggest that increasing that number to another number which is not too high actually can increase the throughput significantly. This slide explains what the final system sort of looked like for those interested in this level of detail. Most people aren't. But essentially there were 3 clusters running. There's the Kafka cluster. We ended up with 9 nodes in that. The Cassandra cluster, 48 nodes, and the Kubernetes cluster. We ended up with 2 virtual machines with 72 cores in total for that part of the system. Okay, as we scaled out, this currently actually is the fastest car in the world. It does 0 to 100 in 2 seconds, and it's also electric, which I think is cool. So let's see how the scaling worked. So we ended up scaling from 3 to 48 nodes, not all at once. We did increase incrementally and retuned as we went. So this got us the magic number of 19 billion checks a day. Again, there's no upper limit. We could have increased the system size significantly if we'd wanted to. In terms of the resource usage, so this is basically just showing visually that for the biggest system we used 574 cores. Cassandra was by far the biggest resource hog, followed by Kubernetes and Kafka. 67% of the cores were for Cassandra, and the rest for the other 2 parts of the system. Similar graph showing that. So the other aspect of this is the affordability at scale. Because we could incrementally change the size of the system and tune it for each size, we were able to achieve what we were hoping to in terms of the cost benefit aspect. So the biggest system was only costing $1,000 a day. That was just in terms of the AWS instance costs themselves, not including the insta-cluster management cost, which we add to that. And on the other hand, the smaller system of 3 nodes was only $100 a day. So the system can be sized depending on the business demand. I mentioned that one of the use cases was using Kafka as a buffer. Well, it worked pretty well for that, so it certainly acted as a very effective buffer. We were able to increase the events coming in up to 2.3 million events a day. The rest of the pipeline just kept on processing at the 220,000 events until all the events were finally processed and it caught up again. Why would you do this? Well, in some cases you just may not be able to, or it may be too slow or too expensive to increase the size of the rest of the pipeline. In this particular application, you could easily increase the application part with the Kubernetes scalability mechanisms. However, resizing Cassandra is actually quite difficult and quite slow, and you'd have to have sufficient warning that you were expecting a load spike this. And you can do it. You can add nodes in our managed Cassandra. It will take time to increase the capacity of the cluster, and it's pretty difficult to go back to a smaller system is the main problem. So Kafka is a really good solution for that type of problem. So the so what part of the question. This is a famous takeaway food van in Canberra. If you're ever there, it's still there. So from the technical side, Kubernetes and AWS X in this case did enable automation of the application. It did take some effort to understand and set up initially. I think they've made the X setup a bit easier in the last few months. But once working, it makes the application deployment fast, scalable, repeatable, and low cost. Prometheus and OpenTracing and Jaeger were critical for debugging, tuning, and reporting the application performance and scalability. It is tricky to monitor applications in Kubernetes, but using the Prometheus operator sort of automated all that setup and the dynamic aspects of monitoring really well. To achieve near linear scalability and maximize the throughput, we needed to optimize the pipeline, in particular in this case by tuning the thread pool sizes and the number of Kubernetes pods. And the goal of that was to minimize the number of Cassandra connections. We found that, sure, Cassandra can cope with an arbitrary number of connections, but there is an impact on the throughput. So you need to try and minimize those. You also need to minimize the number of Kafka consumers because that results in more Kafka partitions, which, as the graph showed, results in lower throughput. And we also needed to maximize the detector thread pool concurrency in order to actually just get the results that we did. So they're a bit of a sort of a trade-off set of capabilities, so you need to keep those in mind. From a business perspective, Kafka and Cassandra enable fast streaming and storage at scale. Our Instacluster managed Kafka and Cassandra service did make it easy to automate the cluster provisioning, including creation, deletion, and scaling, and the monitoring of the clusters themselves, which was quite important for me. I was sort of new to Cassandra and Kafka, so I needed to be confident that the clusters themselves weren't a bottleneck at all in the system. We've got highly available SLAs and proactive cluster monitoring, alerting, and maintenance for production environments as well. It's affordability at scale. You can have low-cost open source and commodity cloud infrastructure. You only pay for what you use in terms of the application and the Kafka and Cassandra clusters, which scale linearly with load, so cost only increases incrementally as well. The application can be easily resized up or down for any workload, and there's no upper limit. And of course, I mean, there's lots more use cases involving applications using Kafka and Cassandra together, and other Apache open source projects as well. So they all work quite well together, and you're only limited by your imagination in a sense as to what you can build. Newsflash. So this wasn't quite the end of the story. So I decided to have a look at geospatial anomaly detection as well, just for fun. So I compared the performance of multiple spatial representations and different Cassandra implementations. I extended the application to detect anomalies over time and space. For example, we wanted to find out if an event was unusual relative to, say, its nearest 50 neighbors, where the spatial dimension wasn't fixed. So a neighbor might be either right next to you or 100 kilometers away, depending on how many were available in a particular area. So I used a few tricks to find neighbors, including just latitude, longitude points and distance calculations, bounding boxes, geohashes, and also some 3D geohashes as well. The different Cassandra implementations I tried were clustering columns, secondary indexes, denormalized multiple tables, and the Cassandra Lucene index plugin. And, so I haven't given you the results there. If you're interested in that, which was sort of an extension of this work, there's another 4-part blog series on our website which goes into the details and the results. So if you're interested in any of this and want to find out a bit more, there's a lot more information online. The whole Anomaly Machina blog series was 10 parts over about 6 months. There's the 4-part geospatial extension. The code itself, the application, is on our GitHub if anyone wants to have a look. It's not particularly clever or well written, but it's a reasonable example of an application that uses both Kafka and Cassandra together. And all of my blogs are available as well. So over 2 years, I've written a fair amount of stuff. Hopefully some of it's useful for the community. And it's all about open source technologies. So hopefully there's a good tie-in to ApacheCon. So finally, some anomalies are easy to detect, hopefully. Some anomalies can be detected given sufficient time. This was a quote some decades after Woodstock had come and gone, I think. Other potential anomalies are harder to detect. So I don't know, this is a few months old, this slide, but a few months ago there was quite a lot in the news about some of the fires burning around the world. And interestingly enough, they were burning in the Amazon, the Congo, and Siberia. And there was quite a lot of discussion about which fires were worse than normal, i.e. anomalies. And it was actually quite hard to work that out. So if you want to detect complex spatiotemporal anomalies reliably at scale with Kafka, Cassandra, and Kubernetes, please feel free to try our managed platform for open source. And if you want to know which was the anomaly in terms of the fires, it was actually Siberia, interestingly enough. So that's it, I think. I think that's about my time. Thank you very much.